Could possible intercept with second stage geoscience.
Boris! Boris!
You're such a geek.
You're saying, slughead?
Nobody screws with Boris Grishenko. Better luck next time. Slugheads. Bang! Go!
7-9. Arm the weapon.
It's an Afrikaans, AAC, augmentative, and alternative communication app you built for your father, who lost his speech after a stroke. Key details: what it does: a PWA, progressive web app, that plays pre-recorded Afrikaans phrases via touchscreen, no speech required from the user, just tapping large buttons while it exists. No commercial, AAC app supports Afrikaans with decent TTS quality, so you built one how it works. Static HTML, JS, CSS with pre-generated MP3s. Microsoft Edge TTS, AFZA Willem Neural Voice, runs fully offline on an Android tablet via a local HTTP server in Termux status. Deployed and in active daily use since April 3, 2026 broader context. It's also tied to a PhD research proposal. You're documenting it as a research case, phase 0 data collection, participant profile, consent, records. Research summary: the problem no validated Afrikaans. AC vocabulary set exists for adult stroke survivors. Commercial AC tools don't support Afrikaans with usable TTS, and South Africa has very few speech-language therapists relative to population. meaning most post-stroke aphasia patients are managed at home by family caregivers with no professional support. The artifact, the PWA you built for your father, is both a practical intervention and the first ESR, Design Science Research, cycle. It exists, it's deployed, and it's accumulating real usage data. The research framing HCI4D, Human-Computer Interaction for Development, framed as an HCI thesis, not a clinical one. The contribution is engineering plus design principles for low-resource African language. AC, not a clinical trial. One clinical collaborator, Prof. Kirsten Tunsing at UPSCOC, is needed to validate outcome measures, but not as a supervisor target. PhD structure, 3 DSR cycles, 1. Cycle 1, Afrikaans, your father, N equals 1 deployed system, 2. Cycle 2, IC Zulu, or Sesotho replication, with recruited participants, 3. Cycle 3, cross-language abstraction, transferable design principles near-term strategy, before committing to a PhD, phase 0. Write the full thesis draft using only your parents as participants. This double functions as a standalone publication, AAC Journal, our African Journal of Disability, and as the formal PhD proposal. Phase 1. Community recruitment, 3 to 6 Afrikaans stroke survivors via support groups, runs after registration. In parallel, why this PhD over the other option? Unisarag, the notes are explicit. The AAC PhD is described as the right PhD higher novelty, virtually no prior work in SA, irreplaceable personal position, deployed system, live participant, personal motivation, and longer shelf life than LLM adjacent work. The RAG PhD is a good PhD semicolon. The AAC PhD is only you can do it immediate data collection priorities 1. Mom baseline interview before her memory of pre-app communication fades 2. Usage log running from day 1-3. Dad's participant profile written up 4. Informal consent record documented. Good. Back to your constraint, it's entirely reasonable, and it actually sharpens the research rather than limiting at the multilanguage DSR replication, cycles 2 and 3. Was the proposed path to PhD level generalizability? Without it, you need a different way to make claims beyond N equals 1. The cleaner approach is Afrikaans community expansion. Recruit 3 to 6 additional Afrikaans-speaking stroke survivors. Phase 1 is already planned, which gives you enough participants to move from this worked for one person to here are design principles for Afrikaans adult AAC in home care. That's a coherent, honest PhD contribution. The scope is Afrikaans. The claim is design knowledge for that specific underserved community, and you don't need to pretend competence in languages you don't know. Afrikaans, AAC for post-stroke aphasia. A custom, augmentative, and alternative communication AAC tool built for a specific user, an Afrikaans-speaking man who lost his speech following a stroke. Comprehension is intact. He can read and use a touchscreen with large targets. No commercial AAC app supports Afrikaans with sufficient TTS quality for a real user. This is a progressive web app, PWA, with pre-generated audio. Microsoft Edge TTS, AFZA Willem Neural, that runs fully offline on an Android tablet. It requires no app store, no account, and no internet connection. Phrases are maintained remotely over SSH by a family member. The app is deployed and in active daily use. V1 deployed April 3, 2026.
Roep vir Francisca asseblief. Noodgeval. Kom asseblief. Ja. Nee. Miskien. Ek weet nie. Wag 'n bietjie asseblief. Ek kry koud. Ek moet toilet toe. Maak die venster oop asseblief. Noodgeval. Kom asseblief. My kop is seer. Die pyn klop. Roep vir Hannes asseblief. Ek wil 'n boek lees. Maak die venster toe asseblief. My brein werk. Ek kan net nie praat nie. Ek kan nie praat nie, maar ek verstaan alles.
This is a screenshot of an AAC, Augmentative and Alternative Communication, device interface, almost certainly staged for comedic or satirical effect, most likely a still from a film, television series, or sketch comedy production, rather than a real assistive technology product. The accessibility wheelchair symbol in the top right header pane and the title bar, assistive text, frame the device as a serious speech generation tool of the kind used by people who cannot vocalize, similar in category to a To-Be-I Dynavox, Proloquo 2 Go, or the system Stephen Hawking famously used. Interface layout, top to bottom and left to right. The header bar carries the application name Chat, with a speech/audio icon at the left edge and a window close Alex control at the right. Below this, the screen is divided into roughly 4 functional regions. The upper left pane is the composition buffer, the message currently being assembled, displaying the partial sentence, "The fuck you ass P," in large white type on a dark blue field. This is what the device would synthesize to speech upon submission. The upper right pane is a word prediction grid, offering 8 candidates triggered by the active SP stem. SP, splitters, spunk, spitting, special, spaced, space, spank. These are arranged in a 2-column, 4-row matrix, size for low precision selection, eye gaze, switch scanning, or large target touch, consistent with genuine AAC ergonomics. The lower left column is a quick phrase bank of pre-stored utterances the user can speak with a single tap. Pass me my protein shake, turn volume up, no cap, turn volume down a GG, I rate that, big dick energy, clean up my shit, GTFO, im rock hard bitch. The lower right region is the manual entry area, an alphabetical order on-screen keyboard, AG, HN, OU, VZ plus comma, and period, with the letter P highlighted as the most recently pressed key. Above the keyboard sits a row of control keys, YN, yes, no, quick toggle, enter/speak, and 2 backspace variants, one labeled with a W, presumably delete word, the other a standard character backspace. To the left of the keyboard are edit/clear and shift, tab, controls. Why this is funny, divided by what it is satirizing. The humor, and presumably the entire point of the prop, derives from the dissonance between the sober, clinical framing of assistive communication technology, a system designed to give voice to people who genuinely cannot speak, and the contents being voiced, a hyper-masculine gym bro divided by Gen Z internet slang persona, issuing aggressive, profane, and sexually crude utterances. The pre-saved phrases collectively sketch a character, someone who lifts weights, protein shake, im rock hard bitch, is fluent in contemporary online vernacular, no cap, GG, I rate that, big dick energy, GTFO, and is generally combative, clean up my shit, the in-progress message itself. The juxtaposition of a vulnerable medical device aesthetic with maximally obnoxious content is the joke. I cannot identify the specific source production from the image alone with any confidence. If you tell me where it is from, I can comment further. If you would like, I can also run a web search to attempt identification. Two distinct engineering problems are being conflated here, and they have very different risk profiles. The phrase bank question is essentially routine. The TTS stitching question, as posed, is technically problematic and merits a hard pushback before any code is written. Frequency-ranked quick phrase bank, the design space is small and well-trodden. The substantive decisions are scoring function, a pure frequency count, FP equals plash text/uses, P large is the naive baseline and behaves badly. Phrases used heavily in week 1 will permanently dominate even after the user's vocabulary drifts. The standard remedy is recency-weighted frequency with exponential decay, $SP T plus text now equals psi sum T plus sin text ma uses P E lambda T part text now TI. Thus, where Waucha lambda Rs tunes the half-life. A half-life of roughly 730 days is a defensible starting range for AAC. Shorter half-lives make the bank feel responsive but volatile. Longer half-lives make it feel stable but stale. This is structurally equivalent to L01.E002, Lee et al., i.e. trans, computers, 2001, and to forgetting curve formulations from spaced repetition literature. Cheaper to implement is an exponentially weighted moving average updated on each use, which avoids storing the full usage log and granularity. What counts as a phrase? The cleanest definition is the exact string the user submitted to TTS, hashed and counted verbatim. Splitting into grams or subphrases sounds clever but invites to failure modes. I. The bank fills with high-frequency fragments. Turn the I want to that are not useful as one-tap utterances, and 2. You lose the user's authorial intent. The whole utterance approach is also the only one that maps cleanly onto whole utterance audio caching, which matters for the second problem below. Near duplicate handling. Pass me my protein shake and pass my protein shake should probably collapse. Cheap options, Levenstein distance with a normalized threshold, or embedding cosine similarity using a small sentence transformer, for example, or mini LM L6v2 with thresholding. The latter is overkill at small scale, but generalizes if you later want semantic clustering of the bank. Cold start and pinning. The bank must be usable on day 1. Seed it with a generic AAC corpus, greetings, requests, yes, no, pain comfort scales, and provide explicit user pinning so essentials never get evicted regardless of score. Without pinning, the algorithm will eventually displace a low-frequency but critical utterance such as, I need my medication, a SQLite table, utterance hash, utterance text, last used talk to score, pinned, with an index on score DC, and a top K query is sufficient. This is genuinely a weekend's work. TTS, word stitching. This approach has been tried for about 3 decades, from roughly 1902. The me-2000 and was abandoned for sound reasons. What is being proposed is as entirely unique congregative synthesis at word granularity, which is the coarsest and worst performing variant. The technical objections are not stylistic preference, they are acoustic. 1. Prosody collapse. A word spoken in isolation carries citation form intonation, flat or falling pitch, fully articulated, with terminal lengthening. Concatenating 10 such words produces a sequence of 10 micro-utterances, each ending as if it were the end of a sentence. The listener perceives this as severely robotic, even when the underlying voice quality is high. This is the reason neural TTS replaced concatenative TTS, not because the unit audio was bad, but because no amount of unit-level quality compensates for absent sentence-level prosody. 2. Co-articulation loss. Phoneme boundaries between adjacent words in natural speech blend. The T in want to reduces, the details in did you palatalizes. Word-level stitching eliminates all of this and produces over-articulated speech that sounds non-native or pathological. 3. Boundary artifacts. Concatenation at word boundaries produces clicks, energy discontinuities, and unnatural silences unless aggressive, cross-fading and pitch matching are applied, at which point you have reinvented half of a 2005 era TTS engine. 4. The cost argument is mostly wrong. Modern TTS APIs charge per character, not per request. Caching individual words to save cost yields trivial savings because words are short, while incurring all the quality penalties above. The only legitimate motivations for caching are latency and offline operation, neither of which requires word-level granularity. The correct architecture for an AAC system is some combination of the following, ordered by what I would actually build. On-device neural TTS as the default path. Web speech API in browsers. AV speech. Synthesizer on iOS or macOS. Text. To speech on Android. Or Piper for embedded/desktop deployments. Quality is now genuinely good. Piper's Eno. Lesac medium voice is hard to distinguish from cloud TTS in casual use. Latency is sub 100 ms, cost is 0, and it works offline. This alone may end the problem. While utterance audio caching, when the user submits a phrase to TTS, hash the text and cache the resulting audio blob keyed by hash. The quick phrase bank entries are then served from cache after first use, instant playback, no synthesis delay, no quality compromise, no concatenation. This is the correct form of the caching intuition. Cloud TTS as a premium tier, optionally, using 11 labs divided by OpenAI divided by AWS Polyneural for a more expressive voice. Again, with whole utterance caching. If for some reason on-device TTS is unacceptable, and per-request cloud cost dominates the design, the granularity to cache is whole utterances, or at worst, whole prosodic phrases, clauses, never words. YAFWAT flags 3 traps to be conscious of before committing time. Building a custom TTS pipeline when a one-line speech synthesis .speak new speech synthesis utterance text call solves the problem. The web speech PI is 12 years old, ships in every browser, and is free. If the deliverable is a working AAC, this is the entire TTS layer. Embedding-based phrase deduplication at small scale. A user's quick phrase bank will plausibly contain 5,500 entries. Levenstein with threshold or even exact hash matching handles this. A sentence transformer is an order of magnitude more code and dependency, wait for no functional gain at this scale. Inventing a prediction model. The screenshot's word prediction grid, SP, splitters, spunk, is non-trivial to do well, and rebuilding it from scratch is a research project. Existing AAC corporate and predictive text libraries, for example Presage, or simply an n-gram LM over the user's own utterance history cover this. Treating it as a separate subproject from the phrase bank is prudent. The core insight, if there is one, the phrase bank and the audio cache should share a key, the utterance hash, making them 2 indexes over the same underlying object. That collapses what looks like 2 systems into one.
The constraints reframe the problem materially. 2 corrections to start, then the substantive analysis. Correcting the premise. Edge TTS is not offline. The Microsoft Edge TTS service, accessed via the rever-engineered RANI 2/Edge. TTS Python wrapper is a cloud WebSocket service hosted on Azure. The AFZA Adri neural, female, and AFZA Willem neural, male Afrikaans neural voices are excellent, but every synthesis request requires a round trip to Microsoft's servers. 1. There is no offline distribution of these voice models. The offline or online distinction is therefore the binding architectural constraint, not a soft preference. The Afrikaans offline TTS landscape is genuinely thin. Confirmed by inspection of project documentation. So the realistic offline Afrikaans choices are MMS, TTSAFR, acceptable, neural, or speak eng, robotic, instant. Both are mediocre on prosody compared with Azure Neural, but MMS is the closest to usable. Why word stitching is worse for Afrikaans specifically? Beyond the general objections to concatenative synthesis raised previously, Afrikaans presents three language-specific problems that make word-level stitching particularly destructive. Phonemic vowel length. Afrikaans contrasts long and short vowels in minimal pairs. Manmoon versus moonaman. Keys I choose versus kiss. Chest. Vowel duration in connected speech is conditioned on adjacent segments and prosodic position. Word-isolated citation forms overlengthen all vowels uniformly, blurring the contrast. The voiceless velar uvular fricative X, the G in gon, berg, exhibits substantial coarticulation with following vowels. Stitched at word boundaries, X initial words after vowel final words produce a perceptible glottal break absent in natural Afrikaans. Productive compounding. Afrikaans, like Dutch and German, freely forms long single-word compounds. Lewensverzekeringsmaatschappij, life insurance company, kinderthuis, koffiebouwkar, that are single prosodic units with one primary stress. The compounding is so productive that the unit you would cache is not the word but this morphemic combination, and the cache hit rate collapses. Any morpheme-level stitching strategy produces obviously wrong stress placement. These are not subjective objections. They are categorical features of the phonology. 6. The correct architecture, hybrid with whole utterance caching. The intuition behind caching is right. The granularity is wrong. The architecture below preserves the cost and offline benefits being chased without the prosody collapse. Properties. Cost. Each unique utterance pays the cloud cost exactly once. The nth repetition is free. For an AAC user whose 50-500 utterance vocabulary stabilizes within weeks, lifetime cloud cost is bounded and small. Offline operation. Anything previously said is available offline at the original quality. Genuinely novel utterances spoken offline fall back to MMS. TTS degraded but functional. When the device next reconnects, a background resynthesis pass can replace MMS rendered audio in the cache with Azure rendered audio for any utterance whose TTS source equals MMS. And play count K, transparently improving cached quality over time. Latency. Cache hits are sub 50 ms playback. Cache misses online are 200 to 500 ms. Cache misses offline are MMS inference time real-time on a modern CPU for short utterances. Shared key with the phrase bank. The quick phrase bank described in the previous turn keys on the same utterance hash. Phrase bank entries are by construction cache hits, instant playback, no synthesis delay, no quality compromise, no concatenation. On word-by-word speech during composition. The hypothesis might sound more fluent if one word is spoken as it is selected conflates two distinct things that have opposite answers in the AAC literature. Listener-facing word-by-word output. Avoid. Speaking each word to the conversational partner as the AAC user produces it sounds worse, not better, in nearly all evaluations. Each word is rendered with citation form prosody, flat or falling pitch, terminal lengthening, producing a sequence of microutterances, rather than a sentence. Pirinen and colleagues note in the broader incremental TTS literature that this is precisely the failure mode neural incremental synthesis was developed to avoid. 7, 8. The exception is when the AAC user explicitly wants a running narration register, e.g., dictating instructions, naming items, a mode worth supporting as an option, not a default. B. User-facing keystroke word echo, auditory feedback to the speaker. Well established. A separate audio channel, typically routed to the user's earpiece, are rendered at low volume. That speaks each character or word as it is selected is a standard feature of letter-based AAC systems and is documented to improve typing accuracy and reduce error rates, particularly for users with visual impairment or fatigue. 9. This is private feedback for composition, not output to the listener. It can use speak eng without any quality concern. It is functioning as a peripheral, tactile equivalent signal, not as speech. C. The actually correct solution. Incremental neural TTS, the modern answer to speak naturally as the user composes, is incremental TTS with look-ahead, not word stitching. They at all 7 introduced a prefix-to-prefix framework that synthesizes speech in an online fashion, achieving constant 1 to 2 word latency with naturalness comparable to full-sentence synthesis. Siki et al. 8 extended this with a pseudo look-ahead generated by a pre-trained language model, removing the need to wait for the actual future context. The mechanism is fundamentally different from concatenation. The neural acoustic model produces continuous spectral frames informed by predicted, not yet typed downstream context, so prosody is correct even mid-utterance. The practical obstacle: incremental TTS is implemented only for high-resource languages, English, Chinese, Japanese, German, in the published literature. Adapting it to Afrikaans would require either retraining MMS, TTS-AFR in an incremental decoding configuration, or fine-tuning an incremental TTS model on a smaller Afrikaans speech corpus. This is a research project, not a feature. Mention only to clarify what speaking as the user composes properly looks like. A pragmatic middle ground, clause-level incremental commit. Without retraining anything, an effective compromise is clause-level submission. The system flushes to TTS automatically at every clause terminating q, comma, comma, semicolon, full stop, or a manual speak partial button. Each clause is synthesized as a complete prosodic unit. So within clause prosody is preserved. The listener experiences shorter chunks, but each chunk is coherent. This addresses the conversational dead air problem at much coarser granularity than word stitching, and works with any underlying TTS engine, including the cache-first hybrid architecture above. Concrete recommendation: use Azure Edge, TTS, AFZA, Adreneural, or Willem Neural as the primary online synthesizer via RANI 2/Edge, TTS. Aware that the API is river engineered and Microsoft can change terms at any time. For any production deployment, budget for migration to the paid Azure Cognitive Services TTS endpoint, which uses the same voices. Use Facebook MMS, TTS-AFR as the offline fallback. Except that quality is degraded. The alternative is silence. Implement a SQ light-backed cache, utterance hash, text, audio blob, TTS source, play count, last used TS. Pinned, shared between the quick phrase bank and the audio cache. They are 2 queries over 1 table. Provide a separate, user-only auditory feedback channel, speak-ang, or letter-level beeps, for composition feedback, distinct from the listener-facing output stream. Implement clause-level, incremental commit as a configurable mode for users who prioritize conversational flow over single utterance polish. Do not build word-level concatenative synthesis. Yafwood flags. Retraining or fine-tuning Afrikaans TTS as a personal project. Even a reduced fine-tune of MMS. TTS-AFR requires a curated speech corpus, 1 hour of clean, single-speaker, phonetically diverse Afrikaans recordings with aligned transcripts, GPU time, and prosody evaluation infrastructure. Plausible doctoral side quest, implausible as an enabling subtask for a working AAC. Voice banking, recording your own Afrikaans voice for personalized synthesis via something like Koki XTTS cross-lingual cloning. Tempting and emotionally resonant, but XTTS does not support Afrikaans as a target language. 3. You would be cloning a voice into one of the 17 supported languages, none of which is what is wanted. Designing a custom predictive text engine for Afrikaans simultaneously with the AAC application. Afrikaans N-gram language models exist, the Wuzzy corpus, NCHLT speech, and text resources from the South African Department of Arts and Culture. Using these off the shelf is sound. Building one is a separate project. On Facebook MMS, TTS-AFR, you are correct to challenge this. I cannot independently verify that this checkpoint exists. My prior assertion was an extrapolation from MMS. TTS covers 1,107 languages, and Afrikaans is widely spoken with extensive Bible recordings. The training corpus, not a verified observation. The Hugging Face, API, and DLF-BayPublicFiles.com are blocked from this sandbox, so I cannot definitively confirm or deny. But my searches did not produce an explicit landing page for the model. And the partial, truncated language list, visible on Hugging Face co-Facebook MMS. TTS jumps from EU to AHK to BSS with no AFR slot where alphabetical sort would place it. The honest verdict, unverified, probably absent. The MMS official supported languages manifest is at https://dl.fbaypublicfiles.com/mms/TTS all. TTS languages, HTML. Running curl against that URL from your own machine will give a definitive yes/no in 5 seconds. Either way, my apologies for the unverified assertion. It was exactly the failure mode the source traceability rule exists to prevent. Corrected offline Afrikaans TTS landscape. Only confirmed existing options. The realistic conclusion is harsher than I implied 2 turns ago. There is no production-ready, free, offline, neural Afrikaans TTS that you can pip install today. The choices are robotic but offline SBGang, paid, Q-Frenzy, or build it yourself by fine-tuning of its class model on OpenSL R32. The third option is a real but non-trivial path, Van Niekerk et al. For explicitly designed OpenSL R32 for this kind of low-cost TTS development. The short utterance observation reframes everything. This is the most consequential point you raised, and it dissolves several of the technical problems I was treating as load-bearing. If the empirical distribution of utterances is dominated by short replies, ja, ni, later, g did vir my, denki, x loose vir coffee, then Average synthesis duration is shorter than human reaction time, so latency hiding tricks like incremental TTS are largely solving a non-problem. Full utterance synthesis of a three-word phrase on MMS or Edge. TTS is 150-400 milliseconds, which is at or below the conversational turn-taking gap measured in spontaneous speech, 200 milliseconds across languages. 5. The cache hit rate becomes extremely high. Conversational language follows a Zipfian distribution. In AAC corpora specifically, Trenka and McCoy 6 report that a small phrase, inventory, covers a disproportionate share of utterances. Combined with a frequency-ranked phrase bank, the marginal request to the synthesizer approaches zero after a few weeks of use. Whole utterance audio caching is doing the heavy lifting. The underlying synthesizer becomes a cold start tool. The prosody objection to word-by-word output partially collapses. If 60 to 70% of utterances are 1 to 3 words, then speak each word as it is committed is equivalent to speak each utterance most of the time. Citation form prosody on a single word utterance is correct prosody. The pathological case, a long sentence chopped into citation form fragments, is rare by your own observation. The right design rule becomes: speak units at the granularity the user actually composes them, with no artificial weighting. The need for true incremental TTS shrinks accordingly. Incremental TTS with lookahead 7.8 was developed for the simultaneous translation use case where input streams in continuously over many seconds. It is overkill for AAC, where the user is producing a 5-word utterance in 10 to 30 seconds via gaze or scanning input. The dead air problem you intuited is real, but its solution is to commit at the user's natural composition, cadence, per word, per phrase chunk, per clause, not to do mid-word frame-level streaming. This means the architecture I proposed last turn is over-engineered for the actual workload. A simpler design suffices. Per unit commit plus aggressive caching. On incremental TTS with lookahead, what is actually shippable for Afrikaans? The published work I cited 7.8 is research code, English, Chinese, Japanese only, not packaged for deployment, and not rechargeable to Afrikaans without retraining. To clarify the terminology, 3 distinct things are often conflated. Concept, what it does, available for Afrikaans. Streaming TTS, synthesize full sentence, omit audio chunks as they're decoded. Reduces time to first byte. Edge, TTS, yes. XTTS, V2, yes, but no Afrikaans. MMS. TTS, yes. Incremental TTS, synthesize on partial input as it arrives, with explicit or pseudo lookahead for prosody. No. Research only, 7.8. Unit level commit, wait for a user-defined unit boundary, word, comma, clause, then synthesize that complete unit. Yes, implementable on top of any TTS. For your stated AC use case, unit level commit is the right primitive. It works with any backend, Edge, TTS, SBGang, or a hypothetical fine-tuned piper. The granularity becomes a user-configurable setting. Commit on equals word speak each word the moment whitespace is entered. Highest perceived responsiveness, lowest prosody, equivalent to your original word stitching idea, but using actual TTS per word, rather than concatenation of cached words. For Afrikaans, this still mangles compounds, kinderthuis typed and committed as 3 words, kinder, te, house is wrong. The user must type it as a single token to be spoken correctly. The system should treat anything between whitespace as one unit, so a typed compound stays whole. Commit on equals punct speak on. Better prosody. Suitable when the user is composing longer thoughts. Commit on equals submit speak only on explicit enter. The classical AC pattern. A radio button or 3-state toggle on the main screen lets the user switch modes per conversation. Predictive text engine for Afrikaans, concrete options. 3 rungs of increasing capability. 1. N-gram language model, CPU, offline 50 MB. Train a 4-gram Nasernay smoothed LM on the NCHLT Afrikaans text corpus 9, and the South African Center for Digital Language Resources, Satellar Corpora. Tools KenLM, battle-tested, map-based for low RAM, or NLTKLM. This gives keystroke savings comparable to commercial AAC predictors 6, Trenka et al. Report 40 to 60% keystroke reduction with 4 grams. Adequate as a baseline. 2. Small local LLM, mobile desktop CPU, offline 1-4 gigabytes. Quantiz Gemma 2-2b, 5.3 mini, Quen 2.51.5b instruct, or Afro-Llama, specifically multilingual African language fine-tuned. Loaded via Llama CPP or MLX, since you have Apple Silicon. These can do next word prediction, sentence completion, and the speak faster style abbreviation expansion. Latency on an M4 Mac Mini for next word prediction is sub 100 milliseconds. The fine-tuning question is whether the base model's Afrikaans is good enough. Gemma 2 was trained on substantial multilingual web data, including Afrikaans, but I would benchmark perplexity on held out Afrikaans before committing. 3. Speak faster paradigm, LL, empowered abbreviation expansion. K at all 10 demonstrate 29 to 60% text entry rate improvements for iGaze AAC users by letting the user type word initials only. KGVJK can jive Veer My Coffee and having an LLM expand the abbreviation in context. This is the most efficient input modality known in current AAC research. The trade-off is dependence on a capable language model with conversational context. The cited work was English only with fine-tuned LLMs, but the architecture is language agnostic. For your stack, an interesting hybrid is N-gram LM for the always available, always fast baseline. Local LLM as the suggestion engine when on Apple Silicon. Cloud LLM. Claude GPT for the highest quality speak faster style expansions when online and the conversation has context. The key correction from my previous turn, the cache is the architecture, not an optimization on the side. The TTS engine is whatever is available. The cache is what makes the system feel responsive and fluent over time. Yafwats. Building true incremental TTS for Afrikaans. This is a publishable research project, not a feature. 2 doctorates worth of work between fine-tuning a VITS class model on OpenSLR32 and adapting Ma et al. Z prefix to prefix framework. Given your existing PhD on RAG and the unrelated dissertation focus, this should not be the project. Fine-tuning a Piper or XTTS Afrikaans voice. Tractable 40-60 GPU. Hours on a single 4090. OpenSLR32 has 36 hours of cleanish data across 9 speakers, but it is its own multi-week project with audio quality evaluation overhead. Defensible only if the offline Afrikaans gap is the binding constraint on the product. Building an Afrikaans LLM from scratch. Don't. Use Gemma 2, Phi 3, or a Sadilar fine-tuned variant. The Afrikaans NLP ecosystem, Saddler, Stellenbosch TEXTEXT, NWU, has published checkpoints. Survey those before training anything. Reimplementing word prediction without consulting Presage. Presage is a mature C++ predictive text library used in AAC for 2 decades. The South African Afrikaans language packs may exist in its model repository, or be straightforward to generate from NCHLT data. Hat changes when target equals SPWA on low-end Android. Layer, constraint, implication. Runtime, browser only, no Python, no native binaries, MMS. TTS via PyTorch is out. Piper native is out. Anything requiring local Python is out. CPU, ARM Cortex A53 1.3 GHz, typical, 2 to 3 GB RAM, Transformers JS running a 140 MB VIDS model on CPU, is borderline at best. Single utterance inference, probably 2 to 5S on a low-end tablet. Unusable as primary path, possibly viable as offline fallback if quantized aggressively. No local LLM. TTS access, web speech API, fetch WebSocket, WASM, Edge. TTS reachable only via a proxy, Microsoft enforces and origin header browsers, cannot set, confirmed. 1. Web speech API can access on-device engines if the user has installed AFZA voice data. WASM ports of SPEAK Eng ship for browsers 2, 3. Storage, IndexedDB, Cache API, Origin private file system, OPFS, all viable. OPFS is the strongest option for large audio blobs on Chrome 102. Storage can be evicted under pressure unless you request Navigator storage persist. Network, intermittent, sometimes none for weeks. Cold start risk is the single biggest product risk.
Sign-in is required to continue with this premium voice. Or, if you prefer, you may switch to a free, unlimited voice. Sign-in is required to continue with this premium voice. Or, if you prefer, you may switch to a free, unlimited voice.
Sign in is required to continue with this premium voice, or, if you prefer, you may switch to a free unlimited voice.
HLU owns SNDRS, XNMKFRMK5ND.
Hallo, owns S-Nings, XNMNFRM Dolk.
Hel ons nou doorgaan maak vir my koffie nou dadelik. Hel ons nou doorgaan maak vir my koffie nou dadelik.
Three technical notes that matter for implementation. On the edge, TTS proxy. Microsoft tightened the API to require an origin header browsers cannot set. The workaround is a Cloudflare worker that adds the header server side and forwards the WebSocket to Microsoft. Reference implementation. DI IGID Cloudflare Edge. TTS4. Cloudflare's free tier, 100K request stay, is comfortably enough for a single AAC user even before caching. The worker also gives you control to swap to paid Azure Cognitive Services TTS later without changing the client. On capturing web speech, API output. The speech synthesis utterance interface outputs directly to the device speakers with no built-in way to capture the waveform. Media stream track-based capture is not portable 5. This means Tier 2 plays through Google's engine, but cannot populate the cache. The architectural consequence, a user who is offline only for an extended period and never has internet will accumulate no cache improvement from repeated utterances. They will keep hearing the Google TTS rendering. Acceptable. On S01.E002 wasm Afrikaans. S01.E002 ships Afrikaans, AF, as a supported language, 6. The Chrome OS port, WebAssembly plus Audio Worklet 2, and the NPM S01.E002 package 3 are both well maintained. Bundle size is 3 MB, including the Afrikaans phoneme data. Quality is robotic but intelligible. Adequate as a speech is better than silence floor. The 30-day cold start problem deserves direct mitigation. You acknowledged the warm-up window, but 30 days of internet before this works well as a significant product risk for the realistic target user. 3 layered mitigations, each independently effective. 1. Bundle a pre-synthesized starter pack with the SPWA install. Identify 100 to 200 essential Afrikaans utterances, greetings, yes, no, pain comfort, basic needs, common social phrases, names of household members, synthesize them at build time using Edge, TTS, and ship the audio as opus-encoded blobs in the SPWA install. At 30 kilobytes per opus blob, this adds 3 to 6 MB to install size, trivial, and means day 1 offline coverage of the most likely utterances. The starter pack should be derived from published AAC core vocabulary research. 7. Adapted to Afrikaans. 2. Provision time cache warming. For an AAC deployment, the deployer, you, or a clinician, or a family member, is typically present at device handover. Build a small companion desktop tool that takes
sprinkler and bees. You can do it. You can do it. You can do it. You can do it all night long. You can do it. You can do it, Nicky. Kick him in his hairy balls. You can do it. Cut his freaking balls off. You can do it, Ozzy. Bite his freaking head off. You can do it. Cut his fucking head off. You can do it. Get that old ass of yours in the end zone.
Takes a list of expected user vocabulary, synthesizes On S speak eng wasm Afrikaans. S speak eng ships Afrikaans, AF, as a supported language, 6. The Chrome OS port, WebAssembly plus Audio Worklet 2, and the NPM SPEC eng package 3 are both well maintained. Bundle size is 3 MB, including the Afrikaans phoning data. Quality is robotic but intelligible. Adequate as a speech is better than silence floor. The 30-day cold start problem deserves direct mitigation. You acknowledged the warm-up window, but 30 days of internet before this works well as a significant product risk for the realistic target user. 3 layered mitigations, each independently effective. 1. Bundle a pre-synthesized starter pack with the SPWA install. Identify 100 to 200 essential Afrikaans utterances, greetings, yes, no, pain, comfort, basic needs, common social phrases, names of household members, synthesize them at build time using Edge, TTS, and ship the audio as opus-encoded blobs in the SPWA install. At 30 kilobytes per opus blob, this adds 3 to 6 MB to install size, trivial, and means day 1 offline coverage of the most likely utterances. The starter pack should be derived from published AAC core vocabulary research. 7. Adapted to Afrikaans. 2. Provision time cache warming. For an AAC deployment, the deployer, you, or a clinician, or a family member, is typically present at device handover. Build a small companion desktop tool that takes a list of expected user vocabulary, synthesizes everything via Edge, TTS, and produces an OPFS importable cache blob. Transfer to the tablet over USB or via any NAP import. This pattern is unconventional for SPWAs, but standard for AAC products and entirely justified by the use case. 3. Opportunistic background sync. Register a service worker background sync event. Whenever the device has connectivity, the worker iterates over any cache entries, tag TTS source equals SPEAK, low quality fallback, and resynthesizes them via Edge, TTS, replacing the cache entry transparently. The user experiences quality improvement over time without noticing the upgrade. Background sync API support on Android Chrome is reliable. On AOSP without Google Services tablets, fall back to a foreground sync on App Open. Together, these reduce the meaningful cold start window from 30 days to roughly day 0 coverage of common utterances, with quality improvements happening invisibly thereafter. Predictive text engine for the browser. Rule out anything requiring a local LLM on this hardware. 2 layers. Always available baseline. 4 gram Naserne LM in IndexedDB. Train on NCHLT Afrikaans text corpus, 8, plus Talkamisi corpus plus Afrikaans Wikipedia. Serialize to a compact binary tree, 20 to 40 MB, load lazily into IndexedDB on first run. Query latency on low-end ARM, sub 10 ms per next word prediction. Implementation, a custom JS port, or compile can LM to WASM, more work but well-trodden. This gives the 40 to 60% keystroke savings Trenka et al. Demonstrated 9. Online enhancement, Cloud LLM for abbreviation expansion. When online, send the conversation context plus the user's partial input to a small fast model, Claude Haiku, GP-40 Mini, or Gemma 2- to be served via a CF worker, and offer speak faster style abbreviation expansion 10. Critically, this is additive. The Ngram baseline always provides suggestions. The Cloud LLM provides better ones when reachable. Never block the UI waiting for the LLM. For Afrikaans Student models, specifically, Afro Llama and Incuba LM cover Afrikaans, among other African languages. Check their quality on representative AAC inputs before committing to one over a base multilingual model. Concrete framework recommendations for low-end Android. Layer, recommendation, reason. UI framework, Svelte Kid or Preaked, smaller bundle, less runtime overhead than React. Compiles to efficient vanilla JS. Critical on weak CPUs. Service worker, workbox, mature, well-documented caching strategies. Handles update lifecycle correctly. Storage abstraction, DexyJS, 20 kilobytes, for IndexedDB. Native OPFS API for audio blobs. Dexy removes IndexedDB's awkwardness. OPFS is the right tool for large binary data. Audio playback, web audio API with audio context. Needed for low latency cached blob playback. Also where you decode Opus. SPEAK WASM, Echo Garden Project, SPEAK Engem Scriptin, 11, or the Chrome OS port, both maintained. Chrome OS port has audio worklet integration. Edge, TTS proxy, self-hosted Cloudflare worker, OpenAI compatible interface. 4, avoids dependency on third-party proxies. Free tier sufficient. LM format, Ken LM binary, or custom tree. Tree wins on cold start memory. Ken LM wins on linguistic correctness. YAFWIT specific to this delivery model. Service worker eviction. Chrome will evict service workers and storage under pressure unless Navigator storage persist has been requested and granted. It can be silently denied. On day 1, the SPWA must request persistence, and the UI must surface failure if denied. Without persistence, a single low storage event can wipe the audio cache, and the 30-day rewarm starts over. Audio autoplay gesture requirement. All browsers block audio playback until a user gesture. The SPWA design must ensure the first play happens off a user tap, G, the speak button, not autoplay on page load. Google TTS AFZA installation friction. Tier 2 requires the user or deployer to navigate Android setting system languages and input text-to-speech output Google install voice data Afrikaans. This is a one-time setup but easy to forget. The SPWA's onboarding must check speech synthesis, get voices, for lang equals AFZA, and walk the user deployer through installation if absent, with screenshots. WebView versus Chrome. If the SPWA is wrapped in a WebView, e.g., via trusted web activity for Play Store distribution, web speech, API availability, and OPFS quotas differ from standalone Chrome. Test on the actual target device, not just desktop Chrome DevTools. Building a custom ngram tree before checking presage. The presage library has been the AAC community standard for 2 decades. Check its model format and Afrikaans data availability before writing a custom tree loader. Even if the runtime needs to be JS native, presage's data formats and corpus selection are well worth inheriting. You're right to push back, and I owe you another correction. I conflated two different things called Google TTS. Google Translate Cloud TTS, the translate.google.com Translate TTS endpoint, does serve Afrikaans audio. Google's on-device Android TTS engine, calm Google Android. TTS, does not ship Afrikaans. These are different products. The Google TTS languages NPM list I referenced earlier is the Cloud Translate endpoint, not the on-device engine. Let me verify the on-device situation properly before proposing the next pivot. Investigated Android TTS limitations, restructured architecture accordingly. Investigated Android TTS limitations, restructured architecture accordingly. You're correct, and I owe you a clean retraction. The on-device Google TTS engine for Android does not include Afrikaans. I conflated two separate Google products. Translate.google.com Translate TTS, a cloud endpoint that does serve Afrikaans audio. This is what the Google TTS languages NPM package I cited last turn actually lists. Calm Google Android. TTS Google's on-device Android TTS engine, with a much narrower language set that omits Afrikaans. The empirical situation, verified across multiple sources. Android TTS engine, Afrikaans support, notes. Google, calm Google Android. TTS no, confirmed by absence in Android settings. Responsive voices, own Afrikaans documentation states Chrome op Android understoon, nigh the native Afrikaans voice, 1. Third-party AAC language learning developer Grovo lists Afrikaans among languages, with no known Android TTS engine available too. Samsung TTS, no. RH voice, no, covers 25 languages. Afrikaans not in the list, though Tswana is, oddly, 3. SBGang, F-Droid, yes, F4, robotic. User must install APK and set as system engine in Android settings. Vocalizer a cappella read speaker, yes. Commercial, a cappella Tracy Afrikaans voice. Read speaker confirms support, 5, per device licensing. So the Android native TTS landscape for Afrikaans is genuinely empty of free production quality options. This was a real research gap. I should have surfaced 2 turns ago, rather than asserting Google TTS as a fallback. Architectural consequence. Tier 2 collapses. The web speech, API path, I drew last turn assumed the device had an on-device Afrikaans voice the browser could enumerate. On a stock low-end Android tablet, speech synthesis get voices will return 0 results for lang ===AFZA. The tier disappears. Revise stack. Tier 0. OPFS audio cache, always available. Tier 1. Edge. TTS via CF proxy online, high quality, Azure AFZA neural. Tier 2. Removed. Tier 3. SBGang, WASM bundled only offline path, robotic, 3 MB. The simplification is real, no web speech, API probing, no Android settings walkthrough in onboarding, no engine availability branching at runtime. The cost is that the only offline path is robotic SBeak, which raises the stakes on everything else. What this forces? The pre-bundled starter pack and provision time cache warming are now non-optional, with no graceful degradation neural option. Anything not in cache when offline is SBeak. Cache coverage is the product. 3 changes from last turn. Expand the starter pack from 100 to 200 to 500-1000 utterances. AAC core vocabulary research 6 consistently finds that 80% of conversational utterances draw from a few hundred high-frequency phrases, covering 500-1000. Pre-synthesized utterances means most user novel utterances are either in the set or close to it. At 30 kilobytes per opus blob, 1000 utterances equals 30 MB of audio shipped with the SPWA install. On a 16 gigabytes tablet, this is rounding noise. The install itself is still well under 50 MB. Provision time warming becomes the design assumption, not the safety net. Before device handover, the deployer, you, a clinician, a family member, sits with a prospective user, collects a list of expected phrases, names of family members, regular medications, pet names, recurring needs, typical conversation openers, and synthesizes that list against Edge, TTS on a desktop. The resulting cache is transferred to the tablets, OPFS via an import mechanism in the SPWA. This is unconventional for PWAs, but standard for AAC products. The AAC literature treats this kind of personalization as a clinical responsibility, not a technical edge case. The opportunistic background resynthesis from SBeak to Edge. TTS is now genuinely important, not a nice to have. Whenever connectivity appears, every cache entry tagged TTS source equals SBeak is a candidate for silent upgrade. 1 escape hatch worth flagging. Hybrid app. The SPWA constraint is largely a deployment simplicity preference. If at any point the SBeak only offline quality becomes the binding complaint, the next step is wrapping the SPWA in capacitor or a trusted web activity and bundling a native TTS component. Native SBGang via Android JNI, same engine quality as SBeak WASM, but faster on low-end CPUs, less battery, lower latency. Bundled native ONNX runtime plus a fine-tuned VIDS model. Bundled native ONNX runtime plus a fine-tuned VIDS model on OpenSL Hour 32 gives a genuinely good offline Afrikaans voice. Costs you a one-time 40 GPU. Hour fine-tuning effort plus carrying a 140 MB model in the app. This is the only path I can see to neural quality offline Afrikaans TTS without commercial licensing. Licensed commercial voice, a cappella, read speaker, per device licensing, not realistic for a personal open project. None of these is needed for V1. They are explicit upgrade paths if the SBeak floor proves intolerable. Updated Yafwits. Walking the user through SBeak APK installation in Android settings. Don't. If you're going to require a native Android engine, you've already left SPWA territory, wrap the app and bundle it instead. Trying to detect at runtime whether a system Afrikaans engine exists. Save the effort. On stock Android there isn't one. Go straight to the WASM fallback. Investing in offline TTS quality improvements before validating cache hit rate. The empirical question, what fraction of utterances actually miss the cache after 30 days of use, should be measured before any work on the offline tier. If cache hit rate stabilizes above 90%, the quality of the offline tier matters little. If it's 60%, the offline tier is the product. That's a reasonable pragmatic compromise, and it actually restores a tier I had prematurely written off. Let me verify the specifics before refining the architecture. Validated SBake deployment strategy and outlined implementation checklist. Validated SBake deployment strategy and outlined implementation checklist. Good, this is a clean compromise and restores a meaningful tier. The architecture simplifies in some ways and gains one specific subtlety in another. What's confirmed? The active F-Droid SBake Android Engine package is Calm Resident SBake, Resage. Dunsport v1.52.0 as of December 2024 requires Android 5.0 plus 1. The older Calm Google Code Eyes Free SBake package is unmaintained. Afrikaans (AF) is included in the standard SBake NG language set 2. Chrome on Android delegates speech synthesis to the configured system TTS engine. With SBake installed and set as default, speech synthesis get voices will enumerate AF and 100 others. 3. Get voices on Chrome Android returns empty on first call. The SPWA must listen for the voices changed event before assuming the voice list is final. 3. Revised architecture. Tier 2 is restored, but as a non-caching tier, the architectural shape changes accordingly. Tier 0, OPFS audio cache hit, always available, instant. Tier 1, Edge, TTS via CF Worker online, populates cache on miss. Tier 2, Web Speech API F, SBake offline, plays through but cannot cache. Tier 3, removed, native SBake supersedes WASM. SBake WASM bundling can be dropped from V1. The native engine is faster on weak ARM CPUs, no WASM JIT overhead, no audio worklet pipeline, more battery efficient, and removes 3 MB from the SPWA install. The only reason to revisit WASM bundling is if a user accidentally changes their system TTS engine, and you want a guaranteed fallback, which is better handled by detection and reprompt at the application layer. The Web Speech API caching subtlety. Speech synthesis speak plays audio directly to the device speakers and does not expose the synthesized waveform. There is no portable way to capture it for storage in OPFS. 4. The naive consequence is that Tier 2 utterances never enrich the cache, so a user who stays offline for weeks accumulates no quality improvement on repeated phrases. The clean fix is to decouple what is logged from what is captured. Every committed utterance is logged in IndexedDB regardless of which tier serves it: utterance, text, hash, last used TS, play count, TTS source. On any cache miss, the dispatcher checks tier preference and serves audio. A background sync worker, when the device next has connectivity, iterates over log entries where TTS source equals edge and play count K, requests edge, TTS synthesis for each via the Cloudflare worker, and writes the resulting audio to OPFS. The next offline session for that phrase upgrades silently from SBake to edge. TTS quality. No audio capture needed. The log entry is the cache warming signal. This pattern is also better behaved on power and bandwidth. Warming is opportunistic and batched, not a synchronous side effect of every utterance. Provisioning checklist for device handover. A concrete sequence the deployer follows once per device. Install F-Droid client one time. Install Calm Resident SBake from F-Droid. Android settings accessibility text-to-speech output set preferred engine to SBake. Within SBake settings, confirm AF voice variant is available. Test with the SBake built-in test phrase. Open the SPWA. Onboarding screen runs an availability probe. Calls speech synthesis, get voices, waits for voices changed. Filters for lang starts with AF. Surfaces green red status to deployer. Deployer initiates cache warming. Is available. Test with the SBake built-in test phrase. Open the SPWA. Onboarding screen runs an availability probe. Calls speech synthesis, get voices, waits for voices changed. Filters for lang starts with AF. Surfaces green red status to deployer. Deployer initiates cache warming. Paste or import the user's expected vocabulary list, names of family members, regular medications, common needs, conversation openers. SPWA iterates the list against the Cloudflare worker edge. TTS, storing each rendered opus blob in OPFS. Optionally, deployer activates pinning on critical phrases, medication names, emergency phrases, so they're never evicted under storage pressure. Navigator storage persist, requested. Surface failure to deployer if denied. Steps 1 to 4 are Android system actions. Steps 5 to 8 are NAP. The SPWA's onboarding flow should be designed to require this checklist to be completed before the main interface becomes usable, with explicit visual confirmation at each step. Architectural escape hatch is preserved. The structure above is deliberately neutral about future upgrades. The TTS dispatcher is the only thing that knows about tier selection. Replacing Tier 2, native SBake, with a future native engine, a cappella, read speaker, a custom-trained Piper Afrikaans model, is a one-component change. The log-then-resenth pattern works identically whether Tier 2 is SBake or something better. Only the quality differential during the sync upgrade changes. The transition from SPWA to a capacitor-wrapped hybrid, if the SBake quality eventually becomes the binding complaint, is a packaging change, not an architecture change. The cache, the phrase bank, the predictor, the dispatcher, all transfer unchanged. Yafwets, delta from previous turn. Bundling SBake wasm as redundancy, drop it for V1. Adds complexity for an edge case. User accidentally changes system TTS engine, better solved by detection and reprompt. Attempting to capture web speech, API audio for caching, don't. The log-then-resenth pattern achieves the same end without fighting the API. Skipping the voices changed event handling, common bug. First call to get voices on Chrome Android usually returns empty. Treating that as no Afrikaans installed produces false negatives in the onboarding probe. Forgetting navigator storage persist, same warning as before. More important here, because the cache is now the entire quality improvement mechanism.
too far to back down now. Dig deep, stand tall, no fear, no mercy. This is the grind, this is the moment. Show 'em what you're made of.
Here we go again. Goeiemôre, hoe gaan dat met jou? Ek broer graag wappelen. Maak die video op. Ek is onder. Wel, asseblief die dokter. Zie je maar, we gaan niet.
Goeiemôre, hoe gaan dit met jou? Ek wil graag water hê. Dankie vir jou hulp. Ek is honger. Bel asseblief die dokter.
Goeiemôre, hoe gaan dat met jou? 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 Goeiemôre, hoe gaan dat met jou?
shit!